Hello my friends, welcome again to my video channel. Today we will continue our project on the Kenwood TS700S line, and step by step and slowly we are coming to the end of this project. Today we will focus on the alignment. I will do a whole alignment of the transceiver, and I invite you to be also with me on the workbench and to do the same work if you're interested. The realignment, complete realignment, is necessary due to the fact that I swapped all electrolytics and tantalums, so I'm quite sure that I touched some of the trim resistors or caps, and due to the age of this transceiver some components may drift or have drifted, so an alignment is always necessary. And let's do this work. But before we start, I will show you what I have done in the meantime, and I didn't make a video about it. As we can see, I swapped all incandescent bulbs, replaced them by LEDs, by white LEDs. These are a little bit bluish, but it is a white LED, also here and here. Totally there are 5 LEDs, one here, 2 here in the display. Each of the knobs has one. I've chosen different currents for the LEDs. The nominal value is 20 milliamps. Here I have 20 milliamps because the LED is a little bit away from the scale, so I need full power. Here I have 10 milliamps each per each LED, and this one here I had to reduce down to 3 or 4 milliamp due to a very low current, because the LED is directly behind this window and the intensity of this windows was too high. I will do the same for the VFO 700S, but now we will start with the alignment. One hint: when you use LEDs, it's always a good idea to use a sandpaper or a file and to modify the LED, especially the top of the LED, which is in many cases a lens which focuses the light. So it's a good idea to file off this lens with some sandpaper, so the top is more or less flat, or at least it is roughened, so the light coming out of the LED is a little bit more broader and not so focused as with the original LEDs. Well, and now let's start with the alignment. The manual states some test equipment which is needed in the alignment procedure. It's not very exciting. High impedance tester, RF voltmeter. Okay, I will use my scope up to 200 megahertz, no problem. Frequency counter, power supply, power meter, AF voltmeter, AF generator, linear detector. It means an FM demodulator with deviation meter to set the FM deviation, directional coupler, scope, signal generator, stabilized signal generator for very low output levels, dummy resistor 8 ohms, noise generator. That's something a little bit a special thing to produce noise similar to ignition noise. It's to test the noise blanker. I will see what I can do. I have an idea. Okay, let's start with the first topic. That's the adjustment of the power supply. I already have it done when I swapped the electrolytics, but now it is set to check the voltages within to check whether they are within the specification. One example is plus 21 volt. I think is here, yes. 21 volt, plus 9 volt. As I see, should be this one. Yes, it's also within the range. The plus 5 volt is here. Here we should have minus 24. It's for the display. Plus minus 1 volt. This is not relevant. A little bit more negative. Minus 24 plus minus 1.2. And so on. The other are only switching voltages. Supply is okay. Yes. By the way, it's necessary to mention that these voltages here are not correct in case of TX. we should check it in transmit FM and check the power supply regulation. The minus 4 volt goes in case of TX up to 0.36 plus 0.36 volt, the TBL, and the RB line, which is 0.08 in case of RX. It goes down to minus 3.6 volt in case of TX. It's in the schematic written. These values are correct in the schematic. Here it is not correct. It may cause some irritations when transmitting, when making transmit FM. Now we have the adjustment of the carrier board. Carrier board of this here, 2 crystals for LSB, USB, CW and AM transmit. They are aligned for 10.7 megahertz plus minus 1 or 2 kilohertz depending upon the mode. Test point is, as I see here, test point we have to connect a voltmeter, or I will take the scope, and a frequency counter. The scope has a frequency counter which is accurate enough for this purpose. I checked it, so we can do this work now. But the first preparation is to have one channel free from the oscillation of the VFO and now crystal. I removed in channel 11, you see here, blank space, the crystal, so channel 11, when I choose 11, has no oscillation on the heterodyne board here. And I've chosen channel 11. Display is dark, no output. When I go to VFO, we have a display. Again, when I go to channel 10, 9 and so on, it is USB. When I go to FM, it's more precise indication. So that's okay. There is in the display a circuit involved which suppresses the indication when there is no oscillation, neither from the VFO or from the crystals. So the display is dark, that's okay. And when you ever have a TS700S without display, check whether the settings are okay here, or maybe the oscillation is interrupted or bad contacts. Okay, we have channel 11, and now we can start with the alignment. The output of this generator, carrier generator, this transformer should be aligned to maximum. We see it in the background. And this has to be 800 millivolt RMS. This is approximately 1.4 volt peak or 2.8 volt peak. We have here 1 volt per division. That's approximately 3 volt peak. That's the right value, and we can leave it as it is. And now we check the frequency in mode USB. Where we are, we should have 10.6985 megahertz. That's okay. In the mode LSB, we have 10.7015. That's also okay. And in the mode CW, the CW 10.7. In receive, it's the same as in LSB. And when I go to transmit, I've connected the dummy load to the output and low power setting. We should have 10.7006. That's what we have. So the frequency alignment of the carrier board is okay. There was no additional alignment necessary. Now to the adjustment of the FM carrier frequency, 10.700 megahertz. The FM carrier oscillator is this crystal. This is the oscillator coil we have to align with this output. For this purpose, I go back to the beta counter. I have some digits more. The digital counter and the digital scope has only 6 digits, not more. But when you want to measure accuracy with 100 Hertz, you should have a digit for 10 Hertz at least. 1 digit more than you need, so we have a better alignment. So I prefer this one. I can select 1 or 2 digits more. This should be, when I go to send, in RX of course there's nothing. In send, when I go to transmit, this should be 0. And now I can align this coil exactly to the 0 point. Oops, a little bit too much. 110 1 kilohertz, 100 hertz, 10 hertz. This is 50 hertz. We can forget it in FM. That's also okay. Adjustment of the heterodyne board. This board, it's necessary there is an output, a buffer amplifier, which supplies the probe here for the frequency counter, but this buffer amplifier has to be energized with 9 volt by this clip lead. We have here 9 volt. It's useful to use a voltmeter to check or find the correct pin, and it is fed to this point here on the inductor on the coil, which is connected to the buffer amplifier to supply it. We have here the frequency, and when I remove it, we have no frequency indication. You see it disappears, so we need this voltage and this supply, so we have the frequency, and now we have to set the bands switch to 144, 145, off, normal, reverse, frequency indication according to the scheme. There's a connection here. I'm connected to this point with the counter, and here we have the lead from L9 to 9 volt. This is the necessary lead. This is another version of the TS700S. It's for the K type with up to 147 megahertz. I don't have here. I have here the European version, only 144 and 45. In position 144, where is it? Here is it. It's not mentioned whether the VFO has to be switched off or not. I think there is no difference. Makes no difference. Now the VFO is operative again. Without, I leave it without. Should be, frequency should be 125.100. It's 100 hertz away. I will realign the frequency a little bit. This is L1, and I can align it down a little, some hertz. Okay, that's it. 25.100. That's okay. 145. Also some 100 hertz. Too high. Dot 100, 0. Okay. So repeater switch normal. $125.500. This should be L3. Okay, that's it. Well, don't touch it. And in transmit it should jump up to 126.100. That means 600 kilohertz. Sorry, in receive. Where are we? We are in transmit. Now correct. In receive it should be 126.100 we have, and in transmit 600 kilohertz down. That's it. I fear I have aligned the other ones in the mode transmit, but when I have normal, it's not relevant whether I go to receive and transmit. Correct. I was in transmit mode. Doesn't matter. In normal we have now 26.100 and 125.500. And when I go to reverse mode, Then it shifted 600 kilohertz up. That means when I go from normal to reverse, the frequency shifted 600 kilohertz down in receive. That's good to listen to the input frequency of the repeater, but these frequencies are also okay some hertz away. That's not relevant. The alignment of T1 and T2 for maximum output measured here with the scope is a little bit tricky. The cores are sealed with, I think it's some wax, but very well sealed, so it's a danger to break the core, so I use a small soldering iron. At nominal 12 volt, it is supplied with 10 volt, 9 volt, a little bit less, so I can heat up the core. First I removed with such a dentist tool all the wax I could get, and then I increase the temperature, not to damage the lead. And then I try to move the core. No, it does not move. No. So I will repeat it several times. Until it moves, till it gets warm enough. The core is rather damaged, as I see. There was someone in before. I need a broader tool. Then I think I can have success. Okay, it moves slowly. Very slowly. Always be careful. Such a case. The core is broken rapidly within the fraction of a second. And then you have trouble for many hours. You see, it takes a lot of time. I switch off the camera. It's boring for you to see step by step, millimeter by millimeter. The core was ugly damaged. I didn't get it out, no chance. So I decided to drill a hole from the bottom side into this filter. With my drilling machine I drilled a very small hole, and then I will make the hole bigger, but only by hand, not with a machine, otherwise I would destroy everything. So I can do this step by step, increase the hole until I have a chance to get a screwdriver, my alignment tool in it. The hole has a diameter of 3.5 millimeters, and now, hooray, hooray, the core moves slowly, slowly. Oops, now it does not move. What happens? Gets out, but again I have to be here very careful not to have the problem on the bottom side. I have to go back again. It's very difficult. From time to time it's necessary to clean the thread here on the top side, because some fractions of the core, of the ferrite core, are blocking, so it's helpful to scratch it out to make it clean, and then we can continue with our work. It's a very fragile work. Yes, it moves, but very slowly and very, very careful. Okay, my last option was to take out the filter. I had no other chance to get the core out. This was a shielding from here to here. No chance to bring out the core. It broke also from the other side. I don't know what happened inside this core, but it's an ugly situation, because I've seen before I started my alignment, someone was in there and has tampered with this core, and it was stuck. So a realignment is not possible. Now it's taken out. There's a coil, it's out. We see here this white, I don't know what it is. Is it a glue or whatever it is? Seems to be inside. Lower side I can't see through, but I have to take out now the core carefully without deleting any other windings. It's an ugly situation. The transformer here is in place again. It was a lot of work to get out the old core. I found a new one in my boxes. I've chosen different cores, but they all have the same behavior regarding setting and the frequency or losses. The alignment is a little bit tricky, but now I have the same amplitude, 144 and 145 MHz band. You see the frequency jumps, 125, 126, this is 1 MHz. And now I will fix the cores with some wax. There was a sort of white color or glue which dried out over the decades, and it made it nearly impossible to get out the core without damaging it. Wax is better because wax can always be removed by heat. This is easier for later alignments. Next is to align the output of the VFO. VFO has to be set to 0.800. This corresponds exactly to a frequency of 9 MHz, 9.000. The amplitude should be at test point 2. Scope is connected to it. 300 millivolt RMS. We have here 30 millivolt RMS times 10 by the probe, so this is correct. Next step is to connect the RF voltmeter to terminal 133. The scope is connected to the test point 133 MHz. Here we have the output signal, and now I have to line it for maximum. There are 4 cores, and this is rather easy. This one has not a big influence. And the last one. And to repeat it several times. We'll touch it, this core. Sorry, it's a probe. When I touch the probe. But I think I have to fix it with wax. And now there is the proposal to turn the core of T4 counterclockwise to reduce the output by 2 dB. This is a voltage drop of 20%. I didn't up to now understand what it is. I checked it and now I understand it. It has to do with the output power. In the moment, the output power in FM we have is 12 watt. and in 144 less than 10 watt. But when we turn this last core a little bit counterclockwise, so that this decreases, then we have an increase in the output power. And I think we have to realign the whole chain. But the problem is that the core T4 supplies the voltage for the RF, for the RX circuit and for the TX circuit. There are obviously different impedances, so this alignment of T4 is more or less a compromise. I tried to get the best compromise for the setting of these 4 cores. I also had a look into the transmit output power, but I believe the PA also has to be aligned. I have a little bit of drop of the output in the range of 444.200.300. Maybe the PA needs also some alignment. The next step is to set the output power or output voltage of the VFO. It's done at 145.800. So we see the probe. A crystal has to be installed with 145.800. It's in channel 9. This output voltage is a little bit higher when we have it set to this point. I go to the VFO and it's a little bit less, but I cannot increase the output of the VFO. There's a trimmer inside and it's at the maximum setting. So the VFO is a little bit too less in the output voltage, but it doesn't matter. I think there's a difference of some percent, which is not relevant. So this part is also done. And we can go to the next step. Now step 6, adjustment of counter unit frequency. The counter unit is here. Counter is connected to test point 1. Frequency should be 10.24000 with an accuracy of 10 Hertz. Okay, we have an error of 9 or 10 Hertz. I can trim it down to 0. This is this trimmer. Okay. Did I say it is easy? No. I think I have to move the trimmer back and forth. I do it. Ha! 1 Hertz. The resolution is 1 Hertz. So this is okay. Now test point 2. When I wanted to start the trimmers for the different modes, I've seen that there's obviously an error in the frequency list. Cannot be. It's not possible because for example, between LSB and USB should be a difference of 3 kilohertz. That's a setting in the carrier board. So USB 7201/500 and LSB has to be 7198/500. This is the wrong frequency. And for AM and CW 7199/400. This is the frequency which is stated in LSB, should be here. So these two frequencies are wrong. These are the correct ones. I checked it also with the manual. The difference between CW receive and CW transmit has to be 900 Hertz. That's the difference for the CW tone pitch, which is set to 900 Hertz according to the manual. So these differences are correct and not the value stated here. In AM we have a problem. The shift is 600 Hertz, not 900 Hertz, but I think this is accepted because there is no separate setting for AM. It's the same as CW transmit. Well, I set it. We have the frequencies in AM 199/400. In LSB 198/500, it's 3 Hz above. In USB 201/500, that's 3 kHz above LSB. Now this I switch back to LSB 198/500, 201/500. This is FM 7200, and this is CW. It's the same as LSB receive, and now when I go to transmit mode, the frequency will shift up by 900 Hz, so we expect 199/400, and I go to transmit. I have low power in the dummy load, no fear. 199/400 is expected in transmit, and that's it. So now the frequencies are okay, and the counter is adjusted. In step 7, the VFO unit frequency shall be checked. It is set to 0, and the frequency is 8200 kilohertz or 8.2 megahertz. Should be 000. Go a little bit more left. Okay, that means when we have here 0 and the index is exactly above 0, then we have 8. A little bit too less. When do we have it? Okay, we are some hertz above 999. Well, when I go a little bit further, then we have 000. We are 90 hertz above, no problem. Then let's go to the other end. For example, at 500, short check of linearity. We have 8.7 megahertz. And at the other end we have 1000. $9.200 megahertz. That's okay. The next test is the check of the frequency accuracy related to the output. Set this to FM. We have here FM 145.00. I added the 100 Hz position of the counter. There's a switch in it. We can add it. It's exactly set to 145.000. And when I go to transmit, mode is FM. Now repeater offset. Frequency is 190 Hz above. The limit is plus minus 300 Hz, so we are within the limit. I'm going to tune it a little bit down. Okay, that's 999. I can readjust it, then it's okay. I switch it off, switch it on, and it's again a little bit off frequency. Some 100 Hz are always part of a possible error. It makes no sense. But I will check the other modes for the accuracy due to the a little bit annoying alignment of the frequency counter. So I go to CW. You see the frequency increases by 1.5. That's okay. I go down to 0. And when I switch on the box, I transmit. We see here a frequency jump of 900 Hz. That's the pitch of the CW. The frequency shifted, and we see indication 999.17, or I can tune it here to 0. And then it is 900 Hz above. So we have a pitch tone when we receive the 145.00. We have a pitch of 900 Hz, and we are transmitting at 0 beat. with this pitch. Seems to be okay. FM we already have checked. USB, LSB we will check and receive, and now to AM. Switch box off. This is also exactly the same frequency in AM as we expected. That's okay. So everything seems to be okay. Now I check the USB, LSB. I do it with 0 beat, and I will receive a signal and 0 beat and measure the frequency in the display. But first I do a counter check that the 145.00 here is correct. I connected the generator to the counter, and you see here a difference of 10 or 20 Hertz. This is not relevant. And now I will connect the receiver to the generator. This is a 0 beat in mode LSB. When I increase the setting, that's okay. Now I switch to USB. 3 kHz frequency jump. That's also correct, as it should be. And again we see here 3 kHz jump from here to here. That's a standard frequency jump for USB LSB, for the beat frequency or for the carrier oscillator. And now a small speciality of the transceiver, the mode AM, which is not standard today, but in those days it was a standard for some transceivers. There is a problem. The receive or the reception path uses the Ssb filter for AM, and the AM is a little bit broader than an SSB signal, and the carrier has to be fed through the filter. So the receive frequency is shifted about 600 Hertz. And I have here a modulation signal AM modulated with a frequency of a little bit more than 2 kHz. It is exactly 2 kHz. It is exactly 2 kHz. And you see, when I go to exact 0 beat, the signal disappears. So I have to go a little bit more down. We'll increase the modulation frequency. Now we have 3 kHz, hard to hear. That means we have to do a small off tuning, and this has to be done with the RIT function. When we are exactly on frequency, the tone cannot be heard, and in manual it is stated to use the RIT. So we can hear the modulation a little bit better with more treble. Treble, not trouble. Treble, okay, treble is also incorporated in the mode AM, but it is treble. It's difficult to operate in AM, this unit, because this shift has to be considered. And there are some informations in the manual, but AM is not important today. It's just a piece of the history, not more. But in general, the frequency indication now is okay in all modes. It is as it should, and the corrections in the manual we have here made in the sheet, these corrections are okay, and we can continue. Now a short discussion of the frequency scheme and of the counter frequencies. This is the Ssb filter, bandwidth 2.4 kHz at minus 6 dB, 4.8 kHz at minus 60 dB. Let's start with the FM carrier and AM receive is in the center. The counter is set to 7.2000 MHz. The AM transmit and CW transmit is located here, 7.199400. This is a difference of 600 Hertz between AM receive and AM transmit. And here we have the difference between CW transmit and CW receive. This is 900 Hz. We have here 7.198,500. And this is the LSB frequency. The upper sideband frequency is 7.201,500. Difference is 3 kHz from here to here. These are the frequencies with delta F again 900 Hz. And this means when we have AM receive exactly in the center, this is a bad quality because the bandwidth is only 2.4 kHz and means 1.2 kHz plus minus. This is too small for even for speech. So it is recommended in the manual to use the RIT function to shift the AM receive a little bit into this direction. So we have a single sideband reception with carrier. The carrier is still needed because the carrier is not regenerated. It's necessary to have the carrier, so we can set the carrier here, and then we have a bandwidth of 2.4 kHz for AM. That's sufficient for speech, but this has to be done again with the RIT function. That's it. So the frequencies we have here in the counter frequencies are now okay, and then we can continue with the next step. An additional small note to AM transmit. When we have here the carrier, the modulation, the AM modulation is not done before the filter, so the AM signal has not go through this filter. Only the AM carrier has to go through the filter, and the modulation, the AM modulation, is done behind the filter. In the first amplifier stage behind the filter, it's a dual gate FET, and one gate is used for AM modulation. And I fear it's when you have a look at the IMD in the modulation, I expect a rather bad signal. I will check it with the spectrum analyzer. In the moment I have no measurement, I will do it. But again, the modulation of the AM carrier, AM transmit, is done behind this filter, and there is no frequency limitation. There are only some LC filters with a relative bad quality regarding selection. So I assume that the AM signal is rather broad and not good. Now we are at the end of part 5 of the videos about the Kenwood TS700S line. There is still a lot of work to be done, but we have good progress. Stay tuned, stay healthy, see you on this channel.